In this episode, we connect the lifecycle discipline you have been building to the practical operating style that makes modern software and modern AI systems reliable, which is the set of practices often called DevOps and MLOps. The core idea is that you do not treat deployment as the finish line, because deployment is really the moment a system begins interacting with messy reality at scale. In cloud security and cybersecurity environments, this matters because changes happen constantly, data pipelines evolve, and even small mistakes can create widespread operational noise or blind spots. DevOps emphasizes building, shipping, and maintaining software through automation, testing, and feedback loops, and MLOps extends that mindset to models and data, where the system is not only code, but also learned behavior. Beginners often hear these terms as if they are job titles, but the principles are simply about reducing risk through repeatability and visibility. We will focus on continuous integration and continuous delivery, CI/CD, validation gates, monitoring, and rollback, and we will treat them as safety mechanisms that keep data-driven systems from quietly drifting into failure. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A useful way to begin is to recognize why data and model systems need DevOps-style thinking in the first place, because the failure modes are not always obvious. When you deploy a model, the code may run perfectly, yet the model can still produce wrong outputs because inputs changed, schemas shifted, or distributions drifted. The system can also fail by becoming operationally unusable, such as producing 10 times more alerts than a team can review, even if the predictions are technically consistent with the model. In cloud security, these failures can lead to alert fatigue, missed incidents, and loss of trust, which are hard to recover from once stakeholders believe the system is noisy or unreliable. DevOps and MLOps practices exist because manual deployment and ad hoc fixes cannot keep up with the pace of change, and because you need a repeatable way to verify that what you are about to ship is safe. Beginners sometimes think automation is only for speed, but speed is secondary. The primary benefit is consistency, because consistent processes reduce human error. When your build and release process is consistent, you can trace what changed and why outcomes shifted. This is how you turn a complex system into something you can operate without constant fear. Continuous integration is the practice of regularly merging changes into a shared codebase and automatically testing those changes so issues are detected early instead of accumulating. In a model-driven system, integration includes not only application code but also data transformation logic, feature engineering code, and sometimes model packaging logic. If you allow changes to pile up and then merge them in a rush, you create a large, hard-to-debug set of differences when something breaks. Continuous integration reduces that risk by forcing small, frequent changes that are easier to test and easier to roll back. For beginners, it helps to think of CI as an always-on quality check that runs whenever you change something, ensuring that the system still builds and basic assumptions still hold. In cloud security data pipelines, CI can catch schema mismatches, broken parsers, and failing validation rules before they affect production data. It can also catch dependency changes that alter numeric behavior, such as changes in how timestamps are parsed or how missing values are handled. CI is therefore a guardrail that protects both correctness and consistency. Continuous delivery, sometimes paired with continuous deployment, extends the automation idea to the release process, making it possible to ship changes reliably and frequently. Delivery means your system is always in a releasable state, with artifacts built, versioned, and tested so you can deploy when you decide. Deployment means the system automatically deploys changes after passing gates, which can be appropriate in low-risk contexts, but requires careful controls in high-risk contexts. In cloud security systems, it is common to use continuous delivery with controlled releases because the consequences of a bad release can be serious, such as disrupting access controls or triggering widespread false alerts. The key is that CD is not about deploying constantly. It is about having the capability to deploy safely when needed. Beginners sometimes assume that careful releases must be slow and manual, But automation can actually make careful releases faster because checks are consistent and repeatable. When you can rebuild and redeploy reliably, you reduce downtime and reduce the temptation to apply risky hotfixes in production. CD also supports rapid response when data pipelines change unexpectedly, because you can ship a controlled fix quickly rather than waiting for a big release cycle. Validation gates are the specific checkpoints that prevent unsafe changes from moving forward, and they are one of the most important MLOps ideas because model systems can fail in subtle ways. A gate is a test or set of tests that must pass before a change is allowed to progress to the next stage, such as from development to staging or from staging to production. In data systems, gates can verify that input schemas match expectations, that key fields are present, that missingness rates are within acceptable ranges, and that data freshness meets the required cadence. In model systems, gates can verify that the model produces outputs on known test cases, that performance on holdout datasets remains above a minimum threshold, and that output distributions have not collapsed or shifted in a suspicious way. Beginners sometimes think gating is overkill because the system seems to work, but gates exist because some failures only show up after deployment, and by then the damage is real. In cloud security, gates can prevent a parser change from turning an important action field into nulls, which would quietly break detections. Gates are the difference between controlled evolution and accidental breakage. A particularly important kind of validation gate in MLOps is data validation, because the model's behavior depends on data meaning and shape. Data validation gates can check that categorical values are within expected sets, that numeric ranges are plausible, and that relationships between fields make sense, such as an end time not preceding a start time. They can also check for duplication spikes, join explosions, and other pipeline artifacts that create false signals. For cloud security analytics, these checks protect against both benign changes, like a service update that adds new event types, and malicious manipulation, like an attacker injecting values designed to confuse parsers. Beginners often assume validation is only about catching empty files or missing columns, but the more valuable checks are semantic, meaning they test whether the data still represents the same reality. If a field's meaning changes, a model can become wrong while still receiving data that looks structurally valid. Data validation gates help you detect that kind of shift early, and they provide evidence for why a release was blocked, which supports governance and stakeholder trust. When data validation is treated as a first-class gate, model deployments become far safer. Model validation gates extend the idea by checking the model as a behavioral artifact, not just as code. A model can run without errors and still be unfit for deployment if it performs poorly on key segments, if it has become overconfident, or if it behaves unpredictably on edge cases. In cybersecurity contexts, you might care about performance on rare but important classes, like high-severity incidents, and a small performance drop there could be more important than a larger performance improvement on common benign cases. Model gates can also check calibration-like behavior, ensuring that score distributions remain consistent enough for thresholds to remain meaningful. Another important concept is regression testing for models, which means comparing a new model version to a previous one to ensure the new version is not worse on critical criteria. Beginners sometimes think a model should always be replaced by the newest one, but operational systems often prefer stability, so improvements must be proven, not assumed. Model validation gates make that proof systematic by embedding it into the release pipeline. This is how you prevent performance claims from being based on hope rather than evidence. Monitoring is what happens after deployment, and it is essential because no amount of pre-deployment testing can anticipate every real-world condition. Monitoring for MLOps includes monitoring system health, such as uptime and latency, but it also includes monitoring data health and model behavior. Data health monitoring tracks freshness, completeness, missingness patterns, and distribution shifts, because these are early indicators that input meaning is changing. Model behavior monitoring tracks score distributions, alert volumes, and segment-level performance where possible, because shifts there can indicate drift, leakage changes, or operational changes in the environment. In cloud security, monitoring also includes measuring how outputs are used, such as whether analysts are closing alerts as false positives, whether response times are improving, and whether the model is being bypassed due to lack of trust. Beginners sometimes think monitoring is just watching dashboards, but monitoring is actually a feedback system that tells you whether the deployed solution remains aligned with business needs. Without monitoring, models become stale silently, and stakeholders discover problems only after damage occurs. Monitoring is therefore a form of continuous evaluation, not an optional add-on. A key beginner concept is that monitoring should include leading indicators, not just lagging indicators, because you want to catch problems before they cause operational harm. A lagging indicator might be a rise in confirmed incidents, but by the time you see that, you may have already missed detection opportunities. A leading indicator might be a sudden shift in feature distributions, such as a large increase in missing values or a new category appearing in an important field, which can warn you that the model is about to behave differently. Another leading indicator is alert volume change, because if a model suddenly produces far more alerts than usual, it may indicate a data pipeline change rather than a real threat surge. In cloud security systems, leading indicators help teams respond quickly with investigation and mitigation, such as adjusting thresholds, fixing parsing, or temporarily routing outputs for review. Beginners often think it is enough to monitor accuracy, but accuracy is usually not directly measurable in real time because labels arrive late and ground truth is incomplete. This is why behavior monitoring, data monitoring, and operational impact monitoring are all necessary. A mature monitoring strategy watches the whole system, not just the model. Rollback is the safety mechanism that turns monitoring signals into controlled action, because monitoring without the ability to respond is just observation. Rollback means you can revert to a previous known good version of code, data transformations, or models when a new release causes harm. In model systems, rollback is especially important because failures can affect operations quickly, such as increasing false positives or changing thresholds in unintended ways. Beginners sometimes assume rollback is only for catastrophic crashes, but in MLOps, rollback is often for behavioral regressions, like a model that is technically functioning but operationally worse. Effective rollback requires versioning, because you must know what version you are returning to and you must be able to redeploy it reliably. It also requires clear criteria for what counts as unacceptable behavior, such as alert volume exceeding capacity or key monitoring metrics crossing thresholds. In cloud security, rollback can prevent a release from overwhelming analysts or from missing important detections while you diagnose the root cause. The ability to roll back quickly can preserve trust, because stakeholders see that the team can respond responsibly to problems rather than denying them. Rollback is therefore an accountability feature, not a retreat. It is also important to understand that rollback is not always a single-step action, because model systems often have intertwined components. If you deploy a new model, but the feature pipeline also changed, rolling back the model alone might not restore previous behavior because the inputs are different. This is why coordinated versioning and compatibility checks matter, ensuring that model versions are paired with the data transformation versions they were trained to expect. Beginners can underestimate this coupling and think of models as independent files, but in reality, models encode expectations about feature meaning and distribution. Rollback planning should therefore include dependency awareness, which is the idea that you must roll back compatible sets of components together. In cloud security analytics, that might mean rolling back a parser update and a model update at the same time to restore consistent semantics. Another concept is gradual rollout, where you deploy to a small portion of traffic or a subset of environments first, so you can detect issues before full exposure. Even without implementation detail, the key idea is that rollback is easiest when changes are small, controlled, and compatible. DevOps and MLOps practices are what make that true in practice. The human side of DevOps and MLOps is also worth understanding, because tools alone do not create reliability unless teams use them with clear roles and discipline. Someone must own the release process, someone must respond to alerts, and someone must decide when to roll back, and those responsibilities should not be ambiguous. In security contexts, model outputs can affect incident response, so coordination between data teams and security operations teams is essential. Beginners sometimes imagine that the model team can work in isolation, but operational reliability requires shared understanding of what outputs mean and what actions follow. This is where documentation and runbooks, meaning clear instructions for responding to common issues, become part of MLOps even though they sound non-technical. Clear processes reduce panic during incidents and reduce the risk of making rushed changes that compound problems. A professional MLOps approach treats the system as part of operational security, with defined escalation paths and clear decision authority. That clarity is what allows teams to move quickly without being reckless. Bringing everything together, applying DevOps and MLOps principles means building automated, repeatable processes that reduce risk when you change code, data pipelines, or models. CI/CD provides a structured path from change to tested artifact to controlled release, making it possible to ship improvements without accumulating hidden fragility. Validation gates protect the system by blocking releases that violate data expectations or that regress on critical model behaviors, which is essential in cloud security where silent failures can be costly. Monitoring provides continuous visibility into data health, model behavior, and operational impact, catching drift and pipeline changes before they become incidents. Rollback provides the practical safety net that turns monitoring into responsible action, preserving stability and trust when a release behaves poorly. When these pieces work together, the system becomes an engineered product rather than an improvised experiment, and that is the difference between a model that demos well and a model that can be used safely. For the CompTIA Data AI certification, understanding these principles shows that you can think beyond algorithms and build systems that survive real-world change, which is the true test of professional data work.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.